So now it's time to go back to look at some code again, and we're going to continue working with C++ 11. So this is a repetition from previous. C++ threads are now built into the standard library of the language. So you create a thread. Well, first of all, include the thread header. I recommend that you use using namespace std so that you don't have to write std : thread all the time. So you declare a thread, or in this case even create, by declaring a variable t1 of the type thread, and then you specify a function that this thread should execute, and this one is call from thread, which is defined here. And then the main program calls the join method of this thread, and which means that the main thread will wait here until the T1 thread has finished execution. The T1 thread finishes by sort of just exiting the function that was defined for the thread here. So fairly simple. Declaring a T1 will allocate the necessary data structures for a thread. Initializing it with a function name will create the thread. The operating system will be told to create the thread, and it will be available for execution. In order to use this in your own code, and if you're using G++ or GCC, you need to specify. So far, C++ 11 is not sort of the standard or the default standard of the language that GCC will be using. So you need to specify -std equals C++ 11, and you will have to link with the pthreads library. So the GCC implements C++ 11 down below using pthreads. And then -o will, and this is of course how it's written in Linux and other Unix derivatives. -o will tell the compiler the name of the executable, and then you specify the source code here. In this course, C++ 11 was introduced. I don't know which version of GCC, but in this course, I will like you to make sure that you have GCC 4.9 available in any case, because there are other stuff that we will be using in version that requires version 4.9. So some considerations here. For instance, consider scope. If you have a thread variable that goes out of scope, that will kill the thread. So going back to this example here, if you didn't have the join and instead let the main thread exit, and maybe the call from the T1 thread did not have the possibility to start or even finish executing, then if the main thread exits, then T1 thread variable will go out of scope, and then the thread will be cancelled without having the chance to finish executing. And the solution here is, of course, then to do the join so that main does not exit beforehand. Also, make sure variables accessed in a thread, shared variables, may not go out of scope. So same thing here. Well, this one doesn't do any access any variables, but it's since you use shared variables here, and you can pass pointers to stack allocated variables to a thread, then it might very well be so that a thread is passed pointer to variable that is allocated inside a function, and then this function exits, and the thread still is executing. Then any variable that was shared from that function will go out of scope, and then you will have problems when that thread will try to access those variables. It's a good practice to not specify the number of threads explicitly in the code. I might do that sometimes in my examples here, but that's typically not a good way to do it. If you want to make sure that you run on the maximum number of threads that the hardware can give you, there is a way to find out. You can call this function, and then you find out how many cores, both hardware and virtual cores, like in hardware multithreading, how many cores do you have in this machine? So on Gothmog, this will return 24. On the computer, sorry, it will return 48. On Valarauco, as it is configured at the moment, it will return 24, but because hyperthreading is disabled. But if I enable hyperthreading again, then it will return 48 as well, because each core has dual hyperthreading on Valarauco. Each thread has a thread identity with a particular type, standard thread ID. You can get the identity of the running thread by calling the method getID on this thread, which is referrals to the currently running thread, or any thread variable .getID will return the thread ID. Now, this is typically not a very sort of sensible number in the sense that it goes from 0 and upwards, but it's an ID that can be compared and ordered. So it's guaranteed that threads that are created in a certain order have thread IDs that are also can be ordered in that same way. So you can compare thread ID variables and you can order them. And if two thread ID variables are the same, they refer to the same thread.